As I explained before the break, the pictures show you how large the loss is, which particular objects or categories contribute most to the loss. They also show you a possible algorithm, a sequence of pictures for minimizing the loss function. And the algorithm consists of taking averages in turn, or to use a magic word, reciprocal averaging, or reciprocal averaging. Well, in Dutch it's reciprocal. Okay. By which we mean that first you compute the average of the object scores to find category quantifications, and then, as in the picture up there, you compute averages of the category quantifications to find new object scores. Now that is an exceedingly simple algorithm because it doesn't involve any matrix multiplication at all. You're optimally using the fact that these indicator matrices are only binary, only have zeros and ones, and it is not even necessary to store the indicator matrices. You only have to store the data matrix and sort of implicitly derive by using indices in a smart way where the ones are. So you're exploiting sparseness. And it's a far better idea than computing these P star or C matrices and subsequently computing their eigenvalues. At least in cases in which the problem is really large. For small problems, of course, it doesn't really matter. So the algorithm is simple. It also shrinks, by which I mean that the new configuration of cars that I'm computing here is smaller than the configuration of cars I had in the first picture. That is, if you do this averaging process all over again, then your configuration will shrink to the origin completely. You don't want that, and of course you don't need to do that because we have the normalization conditions to take into account. So if you take the normalization conditions into account, you get an algorithm which I've called algorithm A here. You start with object scores x0, which are normalized. Then you compute in the first step category quantifications, induced category quantifications. In the second step, by averaging. In the second step, you compute new object scores, again by averaging. But in the third step, you normalize the object scores. And I've indicated that with the operator called gram, which is the Gram-Schmidt orthogonalization process, which I will not tell you anything about because it's simply one particular form of defining an orthonormal spanning space for an arbitrary matrix. So this Gram-Schmidt process orthogonalizes or orthonormalizes the matrix X. After you're done, you go back to your averaging. And of course, there should be some stopping criterion here, otherwise you go on all the time, but that can easily be taken care of. This is algorithm A. There again, because we do everything dually, there's also an algorithm B. Which works exactly the same except for the fact that you start with a Y instead of an X. You interchange the two averaging steps and you orthogonalize Y instead of X. And now you use an operator W gram, which is weighted Gram-Schmidt because the normalization conditions on Y are weighted orthogonality constraints. This is the same algorithm, converges to the same values. Oh, it's not the same algorithm, but it converges to the same values for the reasons that I've discussed before the break. It's the same eigenvalue problem you're solving, basically at least with the same eigenvalues. The algorithms both work by applying reciprocal averaging, a concept which was introduced by Richardson and Kuder and Horst in the mid-30s, in a somewhat different context, but closely related context. And I already mentioned the French name, le principe barycentrique, translated as the centroid principle. The key steps in the algorithms, in both algorithms, are these two averaging steps. And the orthogonalization step is, of course, very essential in order to prevent this shrinking. But it is not even necessary to do that every iteration. You could do it every 10 iterations and get exactly the same result, except for rounding error. Now, it looks from the structure of the algorithms that ultimately you're going to have both x in the centroid of the corresponding y's and y in the centroid of the corresponding x's. This, however, is not true, exactly because of this orthogonalization step. Here, it is true that you have x in the centroid of the x's. At this point of the algorithm, it's true that you have y in the centroid of the x's, but not this one anymore. And here, you spoil this one too, and when you go back here, x is okay again, but the other one is destroyed. So you cannot have it both ways. That's the difference between the algorithms. You cannot have both y as centroid of the x's and x as centroids of the y's. One has to choose between one of the principes barycentriques. There's a principe barycentrique for columns, there is one for rows. Homals, which is our program for homogeneity analysis, uses algorithm A. Thus, x is normalized, and category quantifications are centroids of scores of the objects in those categories. This is not necessarily the best option for all circumstances, but it is a very convenient option if you have a lot of objects. If you have a lot of objects, then it's nice to have them normalized and to have the category quantifications, of which there are fewer, as centroids of the corresponding objects, as I will show in some of the examples of the technique. Now, perhaps it's also nice to show you what this small car example gives as the optimal solution. It's on the bottom down here. It's only for variable 1. And for variable 1 you had, it's not necessary to get the data. Variable 1 you had these 3 cars, Dodge Colt, Plymouth Horizon and Chevrolet Chevette in the first category, and the algorithm is able to make that category perfectly homogeneous. There were the Dodge Diplomat and 2 other cars whose names I have forgotten. Were in the second category of this variable. This is also made very homogeneous by the algorithm. The third category is more of a problem. This was AMC Eagle and 2 other cars. They're in the third category, and that category does contribute a little bit loss to the overall loss function. Of course, the Oldsmobile 98 does not contribute any loss because it's all alone in its category. So you can see that the black lines here are considerably shorter than the black lines in the picture above it, which is the loss for this arbitrary solution that I started out with. This is a slightly more realistic example, not much more realistic. And in a sense it's, well, actually it's not more realistic at all. These are the Hartigan's hardware. The screws, nailed bolts and tacks that I showed you yesterday. It's slightly more realistic. I said at first because it's 24 instead of 6 or 10, instead of 10 variables, and there are 10 objects and 6 variables instead of only 3. But of course the choice of objects is extremely arbitrary, and the choice of variables is a little bit weird either, too. I mean, I don't know how you would describe these things, but well, that's more or less the problem, of course. This is the solution of given by the Homals program. Of course, this doesn't show you anything at all, these tables, but the only thing they show you is that one thing that comes out are the object scores. That's a matrix X of 24 times 2 dimensions, because I want a picture in 2 dimensions in the plane. And it also gives you the category quantifications of the 6 variables. It's partitioned because this is y1, y2, y3, until y6. Yes, and in this, the matrix X is standardized. In this case, it's standardized in such a way not that x prime x is equal to 1, but x prime x is equal to 24 times 1. So these are standard scores in the classical sense. They have variance 1 instead of sum of squares 1. And these are centroids. So if you look at the data again, then there's category, let me take an easy one, category 4 of variable 5. There are only object 2, and these objects here are in that category. That means that category 4 of variable 5, which is listed down here, is the average of the vectors corresponding with these objects which are in category 4 here. So this averaging process relates the object's quantifications with the category quantifications. There's something down here which is called the discrimination measures. And the discrimination measures are the variances of these category quantifications of the variables. So you take the variance of each of these pieces, there's 6 pieces, and you do it for each dimension, and you have these discrimination measures here. It's fairly easy to see by using the equation of homogeneity analysis that the average discrimination measure is equal to the eigenvalue. So you want the discrimination measures to be large. You also can say something which shows you that a particular variable contributes a lot to the homogeneity, and some variables, for instance brass, is very inhomogeneous because it has a very low discrimination measure, a very low variance of its category quantifications, both on the first dimension and on the second dimension. These are sort of similar to factor loadings in or component loadings in ordinary principal component analysis. Only in this case, it's not the correlation between the component. These are the components. It's not the correlation between the component and the variable, but it's the multiple correlation or the correlation ratio between the qualitative variable, the dummy coding of the variable, and the component. So these correlation ratios here show you how well a particular variable discriminates or homogenizes on a particular dimension. There's another way in which you can show the results of this example. This is probably almost impossible to read. I hope, well, some of it is still readable. It's also handy to have the data in an immediate neighborhood. This is 6 times the same plot, and it's the object scores. So I showed you the matrix of object scores, 24 times 2. These are these 24 points, tacks, nails, bolts, screws, and whatever they are. The first variable indicated whether the object had a thread or not, yes or no. I've labeled in this first plot all objects with a thread with yes, all objects without a thread as no. And the general idea of homogeneity analysis, of course, is that everything with yes should be close together, and everything with no should also be close together, and the yes and no's should be as large as far apart as possible. So you can see in what sense there is discrimination. If there's discrimination on the second dimension, if there's discrimination on the first dimension, and what direction it is, and what shape, the shape of the cloud of points is corresponding with a particular category. That also explains why I've done it. I've made the same plot 6 times. There are 6 variables. So we take the fourth one, which has again 2 categories. Bottom, sharp and flat. I think something must be wrong there. it says the labels that are used are yes and no, which sort of indicate that this is variable 6. Could be true because this is from another part of the book than this is. But if this is, this would explain the fact that the discrimination measures of brass, which is variable number 6, are very low because the yeses are distributed not separately from the no's. They're completely in between. And it is variable 6 because there are only 4 yeses on variable 6, and they're behind this black bar there. Yes, they're within, immediately between the no's. And this is sharp and flat, which is variable 4. So this is the kind of plot you can make. It doesn't look very interesting for this particular example, but then again, the example is not very interesting. It does show you what kind of plot you can expect from a homogeneity analysis. There's another much more serious analysis, and that's in the handouts that I distributed today. This is a paper by somebody who works in our department on classification of a very sympathetic group of mammals, whales, porpoises, and whales, dolphins, and something else, which I cannot pronounce.
Anybody else not have this besides me?
This is sort of the main picture. The paper is useful for various purposes. In the first place, it gives a short summary of the equations of homogeneity analysis and of the algorithm, so you can use it for that purpose. It also gives an example of a three-dimensional homogeneity analysis. This is a three-dimensional plot of these whales, 36 whales, dolphins, and porpoises. And it also shows you an interpretation. It gives an interpretation of the solution in terms of the biological classification, which is on, I don't have transparency, but it's on page 34 of your handout. That's the current accepted biological classification of these animals into 9 different groups. And it's based on various sources of evidence, both systematic evidence and evidence undoubtedly from evolutionary and paleontological sources. So that particular tree structure is suggested by biological theory, and it's interesting to see that the groups come back in a very clear, or in a relatively clear fashion, in the homogeneity analysis solution, which does not use this information, of course. I mean, the homogeneity analysis does not know this classification into groups, nor does it use it in any way. So this is perhaps a nice illustration to have around. It's also not too long, and there are not too many whales, dolphins, and porpoises around, so it's still possible to separate the wood from the trees, if that's it's a Dutch expression. I don't know if there's an English equivalent. It's taken from this book. Oh, I do have transparency with this classification on it, but you have it now in your handout. The reference is on top of the page of the handout, and this is the classification that the biologists use. There were some problematic, indicated by the biologists, some problematic branches in the diagram, mainly having to deal with these river dolphins up here. And it says in the paper that something about these problematic classifications that you could get from the homogeneity analysis solution. Here's another example which will probably be quite familiar to most of you. This is a multiple choice test given to approximately, it's also in the list of examples that was distributed yesterday, the details about the multiple choice tests. I think it's an introductory psychology course. Yes, it is. 190 students and 30 multiple choice items with 4 categories each, not surprisingly. And what we have done is a homogeneity analysis in 1 dimension. Of course, we have already seen examples now in 1, 2, and 3 dimensions. 3 dimensions is comparatively rare. 1 dimension is sort of special but occurs a great deal, and 2 dimensions is common. So this is a 1-dimensional example which we have not seen yet. And what I've plotted here are the object scores, 1-dimensional object scores, a vector of 190 numbers, against the number of correct answers for these 190 students. And what you see is a slightly convex relationship between the number of corrects. It is the other. It shouldn't surprise you that it's a decreasing function. Of course, the eigenvector is it's not a decreasing function at all. The sign of the eigenvector is undetermined, so you can either plot it as a increasing or a decreasing function. What is sort of surprising is that, I don't know if it's very clear here, but it sometimes happens, and I don't think it actually happens, well, it does happen here, yes. This is the vertical dimension is the HOMAS, the homogeneity analysis scores. And what you see here is somebody with only 3 errors who gets a higher, remember that I took the eigenvalue in the other direction, gets a higher score than persons with 2 and 1 error. So this is something which can happen. Of course, it depends on not only on the number of correct answers that you have given, but also on the whether the item that you answered not correctly was a difficult item or not, or was usually answered correctly by bright students or not. So you can get effects like this in the tail, and of course students over here would be extremely unhappy, perhaps, if they got a lower score than somebody who had more errors. So I'm not suggesting that it's necessarily optimal to copy this scoring system for multiple choice tests, but it does show you that the regular scoring system, which is the number of correct answers, is not necessarily the most logical one, although it may be the most usual one or the most simple one. You can get tail effects such as these. There's another homogeneity analysis here which is very similar, so the same data. But instead of using 4 categories, we used only 2. Well, this is not very nice. Correct and wrong, to be precise. And it shows you a much more linear relationship and a much smaller band, much less spread, which is of course logical because correct and wrong is much more closely related to the number of correct answers than using 4 categories with optimal quantification also of the wrong categories. In Gifi there's a plot of the category quantifications, and you can see how the correct category compares with the wrong categories. For all items it's true that the correct category gets the highest score, but it's not necessarily true that the difference between the categories is always the same for all items. Again, here's this peculiar person who gets the highest score, same score as somebody up here who has more items correct. He gets the highest score and a higher score than 2 people with more correct items. This is also a typical application multiple choice test, but of course very similar application would be to questionnaires with 5 categories of answers or Yes.
How is this related to scalegram analysis?
I will come to that later. Yes. It's closely related to scalegram analysis. As a matter of fact, Goodman developed it as one method of doing scalegram analysis. So in that sense, it's closely related. Our discussion of homogeneity analysis so far has been largely geometrical. Now, there are a number of questions which you could ask yourself. What is the purpose of the technique? If P is larger than 1, we have seen examples of P is 2 and P is 3, then the purpose of the technique is drawing a picture in which objects with similar profiles, similar answer patterns, similar description in terms of variables are close together, and objects with very dissimilar answer patterns are relatively far apart. And in the same way, at the same time, categories which contain roughly the same objects should also be close together, and categories which contain different objects in which different persons score should be relatively far apart. You want both these things at the same time. If P is equal to 1, you do not really have a picture. You have something which could perhaps more appropriately be called a scale. How do you choose P? Dimensionality, that's also a question which you could ask. Well, how you choose P depends on the type of picture that you want. If you want a scale, then you should choose P is equal to 1. If you want a plane projection, then you should choose P is equal to 2. And if you want a three-dimensional plot, then you should choose P is equal to 3. In the case of this Wales example, it's probably in the paper, I'm not sure, but I think so. Both P equal to 2 and P equal to 3 were tried out. And it turned out that P equal to 2 was not enough in the sense that some groups which were distinguishable in the sense that they were familiar to the biologist, they were in the tree diagram, did not occur in the homogeneity analysis solution of P equals to 2, or were not separated. And they were separated in the P equal to 3 solution. So in that sense, P equal to 3 solution is a better, more satisfactory representation than the P equal to 2 solution. But an important point here is that the dimensions are nested, and I'll explain the use of that word. That simply means that the first 2 dimensions of the best 3-dimensional solution are identical to the best 2-dimensional solution. And the first most important dimension of the 2-dimensional solution is identical to the best 1-dimensional solution. So it doesn't really matter your choice of dimensionality in that sense, because you can compute 15 dimensions and that automatically gives you the best 1-dimensional solution, the best 2-dimensional solution, and so on and so forth. This is in rather sharp contrast with some multidimensional scaling techniques, and also with some of the more linear techniques that I will be talking on later, because there the choice of dimensionality is important in the sense that you cannot recover the optimal low-dimensional solution from the optimal high-dimensional solutions. You lose that structure. And the structure, of course, comes from the fact that you're really solving eigenvalue problems which have that property. Are we estimating something? Not necessarily. And neither are we testing something necessarily. Now this means, this statement, that it's not necessary to interpret your screws and bolts and tacks or your whales or your cars as a random sample from the population of such objects. And if that is not the case, then of course the idea of testing or estimating is difficult to justify. In the case in which you have a random sample, there are connections with, again. Okay, thank you. There are connections with the chi-square of independence theory, which I've briefly outlined on this transparency. I will not go into them in any detail, because they're sort of, well, in my from my point of view, they're not very important. This is an algebraic relationship, which is always true, no matter whether you have a random sample or an arbitrary matrix. It says that if you have this function, which is basically the variance of all eigenvalues, and remember, all eigenvalues could be quite a lot. The order of the matrix C, which we shall suppose is smaller than m times k, where k is the number of categories. So there are m times k eigenvalues, and if n is smaller than m times k, the number of observations is smaller than n times k, then there's still n eigenvalues, number of observations. So there can be an enormous number of eigenvalues. The variance of this enormous number of eigenvalues is equal to the sum of all chi-squares of the bivariate contingency tables. All bivariate chi-squares. So this gives a simple algebraic relationship between the chi-squares that you can compute from your birth matrix, from your contingency table, and the eigenvalues of homogeneity analysis. Now this means, of course, that if all variables are independent, and you have a random sample, it states here in green with a large exclamation mark. If all variables are independent, then this quantity up here converges in law to a chi-square with the appropriate number of degrees of freedom, where the appropriate number of degrees of freedom is simply the sum of each of the degrees of freedoms you would get from the individual cross tables. Now again, this merely shows you that these eigenvalues have something to do with chi-square. It's not suggested as a particularly valuable test of the hypothesis of complete independence of all variables. As a matter of fact, I would not consider testing the hypothesis of independence of all variables I would not take the hypothesis itself very seriously in many situations. Obviously violated in almost any interesting situation by definition of interest, by definition of the word interesting. If there's another result which is slightly more usable perhaps, if a variable, a particular variable, j, is independent of the other m-1 variables, then you can compare the discrimination measure. This is this discrimination measure that I was talking about earlier, the variance of the category quantifications on a particular dimension of a particular variable. You can compare this discrimination measure, if adjusted for the eigenvalue of this dimension, with the chi-square with kj minus 1 degrees of freedom. Now kj is the number of categories of variable j. So this is a result which is perhaps useful not as a test of this hypothesis again, whether a variable is independent of all others, because that is a hypothesis which you really do not want to test in most situations, but it gives you a sort of a metric in which you can compare these discrimination measures. You can see from this result that in the situation in which you have a random sample and you have this sort of independence, that the discrimination measures will vary sort of linearly with the number of categories of the variable. If a variable has twice as many categories, then the discrimination measure will usually be twice as large. It also tells you something about the variability of these discrimination measures, because you can compare it with the variability of chi-square. So this is something in which this result can be used, because it gives you a sort of a natural metric in which you can compare discrimination measures of the variables, and which, if you're really interested, you could use to test this hypothesis. Tomorrow we will talk about some, I don't know, some more or less specialized forms of homogeneity analysis, but first I will introduce a somewhat less geometrical approach to the problem, which is more familiar perhaps to people who have been exposed more to multivariate analysis than to multidimensional scaling. And we will restrict ourselves for the moment to the case p equal to 1. So You're interested in one-dimensional quantifications only, as we have already used in the multiple choice example. We have seen in the previous part of the talk that you can define homogeneity analysis in case of one dimension in terms of the matrices C and D, the Bird table and its diagonal, the bivariate and the univariate marginals. In this particular way, you want to maximize this quadratic form while restraining the quantifications by using this quadratic form and this linear expression up here. So you want, let's say, the average variance must be equal to 1, and the quantifications must be in weighted deviations from the mean. Here again, y without any index consists of m small parts, one part for each variable. We are now going to redefine this optimization problem by introducing new variables. And the new variables are alphas and z's. I'm decomposing the y's for a particular variable, k, j numbers, into a normalized part z and a normalization factor alpha. So if I introduce this alpha, I can require without any loss of generality that z is normalized in this way. Remember, here I only normalize the average weighted sum of squares of the y's. Here I normalize each of the z's. And that is possible because I've introduced this alpha here as an extra variable. Now if you substitute this into the expressions up here, then you get this relationship up here. Y prime dy is simply sum of squares of the alphas. And if you substitute this into the quadratic form up here, then you get this, which is a quadratic form in the alphas, and the r's are the correlation coefficients between the quantified variables. Now you have to remember that these correlations are dependent on the choice of z, or on the choice of y if you want to. So they are not constant, you do not know them beforehand, you're also trying to optimize over them. But I have reduced or rewritten this quadratic form in terms of this quadratic form over here, which is somewhat more familiar because it involves the correlation matrix and these weights alpha, which are very similar to component loadings. So R is the correlation matrix induced, I'm using the word induced, by the scores Y. Now the homogeneity analysis problem in one dimension can now be written as maximizing this quantity, which is the quadratic form we had in terms of the R, over alpha n over z, with normalization conditions that alpha prime alpha must be equal to 1 and that all these z's must be normalized. There's no z in here, but that's simply because I have not chosen to emphasize the fact that R is a function of z, which it is, of course. If you have different normalized category quantifications, then you have a different correlation matrix. Now this problem can be simplified by maximizing out alpha. You can compute the maximum over alpha for fixed z. And the maximum over alpha of this expression under these conditions is the largest eigenvalue of the correlation matrix. So this is equivalent to the things stated here below. You have to maximize over normalized category quantifications the largest eigenvalue of the correlation matrix. In words, which is probably what I just said, we want to find quantifications of the categories that maximize the largest eigenvalue of the induced correlation matrix. So this is another interpretation of homogeneity analysis in the case p is equal to 1, which is quite important because it's well, it's very easy if you think about it a little bit to understand what the technique tries to I mean, if you're familiar with correlation matrices and their eigenvalue patterns, then it's easy to understand that this technique tries to find scores for the categories in such a way that the largest eigenvalue of the correlation matrix becomes as large as possible. The matrix becomes as one-dimensional as possible. As much variance as possible is concentrated on the first dimension. So this definition of homogeneity analysis is quite clear. It also suggests immediately many generalizations, because there are also other properties of the correlation matrix that you may want to optimize. And we will meet them in a later stage. I have an example of this, which is in your list of examples, number 15, called Crime and Fear. There are 10 variables. The first 6 are 5-point rating scales, and the next 4 are background variables. The 5-point rating scales have to do with attitude towards punishing criminals. What kind of punishment do you think is appropriate for criminals? There's some horrible alternatives there. Labor camps, of course. But there are also some nice alternatives, such as better employment for potential offenders, social work and rehabilitation, and, well, it's fairly obvious how people have come to choose these particular questions. Now, one thing you can do with these variables, of course, is what many people do, and that's give 5-point scales, give the categories codes 1, 2, 3, 4, 5, and for age, it's also not really a problem what you want to do. For religion, it becomes, religion is one of the background variables. It does become a problem whether Protestant is 1 and Catholic is 2, or the other way around. But, well, usually people can think of something for that too. And occupational status is also, well, it's also considered to be an ordinal variable, and people usually give 1, 2, 3, 4, 5, 6, 7, and then compute a correlation matrix. Now, for some of you, this particular may sound sort of absurd to use a scoring system like that, but it's done in many examples, and it was done in the published version of this research where we got the example from. So you have a correlation matrix. It says here, this is directly from the output of the program. In this case, the program is called primals, which is a one-dimensional version of homogeneity analysis. Of course, it is not our intention to write a separate version for each dimensionality, but if you have a one-dimensional program, it's convenient because it can output other things which are much more relevant in one-dimensional situations. For instance, the correlation matrix before transformation and the correlation after transformation. This is very much like these Charles Atlas ads before and after. This is the correlation matrix before transformation, and much more beautiful and powerful after transformation, of course. Comparing correlation matrices is possible, but would certainly take too much time. The point is, of course, that we also have the component loadings before transformation and the component loadings after transformation. And what happens here is that the correlation matrix after transformation is considerably, well, not considerably, is somewhat more one-dimensional than the correlation matrix after transformation. Here you have 2.2, which is 23% of the total sums of squares accounted for by the first principal component. And here it's 25% of the total sum of squares accounted for by the first principal component. And this tells you, of course, that a particular scoring system that is chosen here is not too far from the optimal scoring system computed by homogeneity analysis, or in this case by the program primals. And the program, of course, also outputs those category quantifications and discrimination measures so that you can compare them with your original quantification measures. And the thing that's most remarkable, perhaps, is that the first 6 variables, which were these 5-point scales, think perhaps even it's first 6 variables. They're all scored in the same order as that you would expect them to score. There's nothing in the technique which actually imposes this order. So it's satisfactory if it comes out in the correct is not defined, but in roughly the correct order. Some small violations such as this one up here, but you would expect such small violations, especially if the categories are not very well filled.
I have a question.
Yes?
A lot of research in the social sciences has shown that the scoring on categorical variables such as what you represented there does not seem to make a whole lot of difference in what the correlations are that you obtain. Are you finding similar things in your examples besides this one?
Yes, well, it depends on the type of variable, of course. If it's a variable such as these 5.
At least the ordinal.
Yeah, yeah. In that case, you very often find that the optimal scores or the optimal quantifications are very different from linear quantifications, but the correlations that are induced by these optimal quantifications are very, very similar to the linear quantifications. So these correlations are very robust. And the reason for that, of course, is that the deviations from the linear quantifications are usually in the tails. And the tails are, by definition, for these variables like this, usually not filled very well. So the really important part is the middle of the distribution, around the central value. That's where the correlation is really determined, as it were. And there the transformations are very often linear, even if they look very non-linear in the transformation plots. But non-linearity is usually because of the tails and because of the categories with only a small number of observations. So the answer to your question is yes, we find very little variation in the correlation coefficients for ordinal variables that are reasonably well behaved. Of course, if they're very skew, or if they're U-shaped or something like that, many other things could happen. But if they're
these crime variables, I'm not familiar with this data set, but I know in general things like that are generally skewed. A lot of clustering in either the lower or higher categories and a few people in the other ones. So,
well, skewed would still be, but even if you have an ordinal variable, it's possible in principle that there would be nobody in category 1, a lot of people in category 2, nobody in category 3, and a lot of people in category 4. In that case, I couldn't guarantee that the transformation would come out right and the correlation wouldn't change a great deal. But if it's sort of well behaved, and even regular skew pattern would classify as well behaved, the correlation coefficient is very stable. And we typically find that, yes.
But for this example, the implication is that the religious variable was essentially scored originally in the right order, right?
Yes, but
There's also not been a similar researcher that chosen radical scoring.
well, typically a researcher in things like that would treat religion as a dummy variable and not try to go to 1, 2, 3, 4.
well, that depends on the technique the researcher intends to use. If he wants to apply principal components, if he wants to use religion as a dependent variable in regression context, he can easily treat it as a dummy variable, of course. But if he wants to use, for instance, Lisrow or something like that, he's in trouble. He has to use it.
Not if it's an exogenous variable, you can just treat it as a fixed stochastic dummy variable. I mean, a fixed dummy variable.
Fixed dummy. Well, that's certainly right from a computational point of view, but not. It's not. It doesn't apply if religion is treated, let's say, on the same footing as the other variables, so possibly as a dependent variable or as any variable in the list of variables that you're entering into your principal component analysis. It's true that if you're conditioning on these categorical variables, then it's easy to treat them as dummies. Yes, but for some techniques, it simply will not be possible to. There's no concept of an exogenous variable for some techniques, so there it does not apply. You were asking something? No. Okay. Oh, you were saying something about this religion, that it was scored originally in the correct order. Of course, you have to remember here that religion is not a very powerful variable. It's number 7. It does not have very high component loadings before transformation. And it also does not have very high components loadings. In fact, it has even smaller components loadings after transformation. So religion does not have much influence on the eigenvalue at all. In fact, the thing that happens is that the transformation process makes the first 6 variables, the attitude scale variables, more homogeneous, and makes the other variables comparatively less important. Certainly true for religion, but also these over here do not become more important. So the first 6 variables become homogeneous. The technique recognizes the fact that you really should be doing principal component analysis on variables which have 2 different origins. Something which is important in connection with any multivariate analysis technique is how missing data are treated. There's a reference to a book by Meulman in your list of references, which is specifically concerned with, well, it's about homogeneous analysis in general, but it's specifically concerned with the treatment of missing data. It has many examples of that. And in that book, 4 different strategies are mentioned to deal with missing data. And I've copied them up here: missing data single category, missing data multiple category, missing data deleted, and there's another one which is not in that book, but which you could also use, and that's called fuzzy coding. But it's slightly more modern. It's not in Gifi, but it's in later publications. Now here's one example of a variable with a single variable. Of course, you're not going to do homogeneity analysis on a single variable, but just to illustrate the concept of missing data. It has 8 observations, and the last 3 are missing, indicated with a question mark. Missing data single category would code these variables in this indicator matrix. The A's are here, the B's are there, the single C is there, and the missing observations are all together in a missing category. That's missing data single category. You have a single extra category for missing data. This is missing data multiple categories. The first part is exactly the same as this part, but now each missing datum gets its own category. And if you remember the Oldsmobile 98, then you must also remember that observations which are alone in their category do not contribute to the loss. So this is one way of taking care of the fact that these missing data do not contribute to the loss. There's another way of taking care of the fact that the missing data do not contribute to the loss. That's missing data deleted, in which you work with incomplete indicator matrices. At some point, a long time ago, I defined complete indicator matrices and promised you incomplete ones. Here's an incomplete indicator matrix, and it's incomplete because some rows do not add up to 1, but add up to 0. That's an incomplete indicator matrix. And we shall see below here in red that you need a small adaptation of your loss function for such situations. This is the example of fuzzy coding. It's also fuzzy handwriting, I'm afraid. The first part is again the same as in all the other parts. The second one, all the elements are equal to 1/3. This, of course, sort of smacks of prior distributions, but it simply means that you don't know in which category the observation is, so you distribute your ignorance equally over all categories.
Let those numbers be other than 1/3, basically sums to less than 1.
There are many examples in which it makes sense to choose these numbers other than 1/3. For instance, in a psychological experiment, you could ask persons instead of do you agree completely, disagree completely, or have no opinion, to distribute 100 points over these 3 categories. And then you can feed that directly into your indicator matrix. And then this would again correspond to the situation of a person who does not have any preference for the categories. But you could also find other numbers here. And there are also situations in which you do not have total ignorance, but you know that this person has scored in either B or C. In that case, of course, you would have 0, 1/2, 1/2 here as the entry in your fuzzy coding. So this is sort of natural, perhaps in some situations, but it does complicate the algorithm. It does not really complicate the mathematics and the formula at all, because these you do not use the fact that G is an indicator matrix, but it does complicate the algorithm, because the algorithm, the reciprocal averaging algorithm, uses this 0, 1 structure of the matrix G in its computations a great deal. So this fuzzy coding does complicate some things. This is the adaptation of the loss function you need, the basic loss function, if you have incomplete indicator matrices. You need a diagonal matrix Mj for each variable, which has on its diagonal either 1 or 0. It has a 1 there if the observation on that variable is not missing. It has a 0 if the observation on the variable is missing. And the normalization conditions of homogeneity analysis are also adapted by using M star, which is the average of the MJs. So if you have this option, missing data deleted, or in general if you're dealing with incomplete indicator matrices, then you need to use this form of the loss function. And of course, the previous form of the loss function, the regular one, all these MJs are equal to the identity, and also MJ average, of course, is equal to the identity. Yes?
Is MJ the alpha GJ, GJ prime?
What?
GJ is this
Yes.
indicator matrix, right?
Yes.
And MJ is the outer product of GJ.
GJ, GJ prime still contains the univariate marginals.
No, that's just...
In this case, GJ, GJ prime is a diagonal matrix of order 3 with elements 2, 2, and 1. And MJ is a matrix of order 8.
Yeah, well, I was trying to define that, so it was an order 8 diagonal matrix that had ones.
5 ones on the first 5 diagonal places and 3 zeros on the last.
Yeah,
That's what it is.
yeah. So does that generalize to like the lower left-hand fuzzy case in some way? You've got other values on the diagonal than MJ?
Well, the basic problem with a fuzzy case is that G prime G is not diagonal anymore. So your averaging process, in which you need dj minus 1, is not simple anymore, because you're not inverting a diagonal matrix but a full matrix there. That's the basic complication for the algorithm. It is clear, it states on this transparency, that these choices, I mean the choices for a particular option of dealing with missing data, have serious consequences. Again, the consequences are illustrated in the Meulman book. But briefly, the most important conclusions are stated in red here. Single category quantification usually suggests more homogeneity than there really is. it's not true that missing data should be put in the same category and should be treated as being similar in some way or another. And the category should be treated as any other category, because they can be missing for various reasons, and missing is not the same as, for instance, having moved, which is perhaps in some context a good category, or being dead, which is in other contexts a very good category to be in. Multiple category quantifications for missing data will usually, at least if there are many of them, will often lead to dimensions which are completely determined by the missing data themselves. And this is of course not something which you really want. If you want to apply data analysis, you don't want to apply missing data analysis, because you want to base your conclusions on what is there and not on what is not there. So in HOMOS and in the other Gifi programs, missing data deleted is the standard option. That doesn't seem to have these disadvantages. It has some other disadvantages, perhaps I can mention them at some other point, but these very serious disadvantages it does not seem to have. The options can also be used in a much more interesting and creative way. I mean, missing data is not interesting, it's a nuisance, but you can also use them in a much more interesting way. And an example I shall give of this is the analysis of the Munzing and Rhine data, which I already showed the first day, yesterday. These graves and the objects that were or were not in graves. I can also illustrate it with Japanese data, but I probably won't because it's already rapidly approaching 5:30. Now remember, the Munzing and Rhine data look like this. They're also listed in your list of examples. Not too many details about them, but some. As number, I have it somewhere here. 21. Archaeological data, presence-absence data. 70 varieties of objects are or are not in each of 59 graves. It already gives away something here at the top, but this is simply to give you an idea of how the data matrix looks like. The ones are ones and the zeros are dots. And this is the indicator matrix, which can be fed into the homogeneity analysis programs. Now there's the variables are binary, and one decision you could make is whether you want to treat the zeros and the ones in exactly the same way, as being categories of the same type. And one consideration that you could have there is that if two graves have the same object in common, then it's likely that they have been dug in the same time. But if two graves do not have the same object in common, then it does not follow that they have not been dug in the same time. It's the same situation which is also familiar in political science. If persons vote in favor of an object of a law, then they are similar. But if they vote against a law, then they can do that for very different reasons, because they're much more conservative than the proposal, or because they are much more radical than the proposal. So you have a sort of asymmetric treatment between zeros and ones, which is very familiar perhaps to those of you who are cluster analysis adepts. And the many similarity measures which have been proposed in cluster analysis for a great deal are determined by an attempt to weight this asymmetric treatment of zeros and ones. Now in the context of homogeneity analysis, this means that you can, in this Munzing and Rhine example, you can treat the zeros and the ones differently as well. You can treat the ones as being really there. They're categories of the single category of a variable, and all zeros can be treated as missing. And this gives you a number of different analyses. I first give the two-dimensional analysis, which produces the familiar horseshoe. Horseshoe is shaped like this, sort of parabolic shape in 2 dimensions. And this horseshoe shape is familiar. I call it familiar because it pops up in applications of multidimensional scaling and similar techniques to archaeological data. And it roughly means that the objects are ordered along this parabolic axis, this nonlinear axis in the plane. And this is considered to be satisfactory if the order corresponds with the order that was already familiar from other sources, if there was an order which was already familiar from other sources. Now, we see here that there is a relatively clear order except for some graves which do not fit into the pattern, both for missing passive, which is missing data deleted. The word passive is used by Mellman. And for missing multiple, which is multiple categories for missing data. But if you look at the solution for missing single, and missing single is the ordinary homogeneity analysis solution, because that means that you create one category for the zeros, and that of course is exactly the same as using complete indicator matrices. So this is the ordinary homogeneity analysis. Then you do not see any clear pattern. So in this case it seems inferior. And another way in which is showing that it's inferior is by comparing these plots. This is the missing single plot. The missing single plot is now based on the one-dimensional solution in which the 59 graves are ordered in the order of the first principal component, the first object square dimension, and the objects are also ordered in the order of the first category quantification dimension. And what you want ideally is a banded pattern which is as small as possible along the diagonal of the graph, because that gives you a clear idea of what the order could be. Now here there's a little bit of structure. There are not many ones here. There are a couple here, but they're concentrated along the diagonal. But the other solutions, which are for missing multiple, and especially the one for missing passive or missing data deleted, are much more regular, much narrower bands. And one thing we could do in this case, in this sense this is an example of a gauge, is to compare it with the archaeological order which Hodgson had established by other means. This is the Hodgson solution, which is more or less serves as the norm here. And this is the single, passive, and multiple order, which is established by homogeneity analysis. If you compare these two columns or rows with this order up here, then they turn out to be very similar. Unfortunately, there are no rank correlations or something like that in the Mellman book, so you have to compare them by sign. You don't have enough time to do that. So, but it's very clear that the single category missing data treatment is extremely inferior, because it goes completely quite a different order, which corresponds not very well with a predetermined archaeological order. So in this respect, the two orders of passive and multiple, which are very much alike, are much preferable to the single one, which is very different. I think we have perhaps time for 1 or 2 questions, but then I will stop for today.
You're not suggesting that's general result.
No, I'm just suggesting that usually in the examples we are familiar with, missing data deleted performs more satisfactory than the other 2 options. And that for examples like this, or this political-logical example that I mentioned but did not show, it makes sense to distinguish between the yes and the no categories. There's a reason why you should want to do that, and if there's a reason, well, then of course you should do it.
Let me remind people that you can pick up the, if you look at, click on the working on leaving a check now or in the morning. $17.98.